The Lexer's job is done. It has sliced raw text into individual tokens, identifiers, operators, semicolons. But right now, all of these pieces are just isolated fragments floating in a void, completely devoid of structural meaning. If we arrange these tokens sequentially to form a standard variable assignment, the machine glides right through it, processing the code without a hitch. But if we scramble the exact same tokens into a chaotic order, the parser hits a wall and throws a fatal error. The Lexer accepted them. These are entirely valid pieces, but the arrangement is mathematically illegal. We could try explaining to the computer that an assignment statement requires a variable on the left and an expression on the right. But computers do not comprehend English descriptions. They require strict objective mathematics to distinguish valid code from broken text. That mathematical blueprint is called a context-free grammar. Parsers do not have intuition. They cannot invent structural logic on the fly. They rely entirely on this rigid specification, written by the language designer, to dictate exactly what arrangements are allowed. Without the mathematical foundation of a CFG, the parser has no instructions for building a tree or performing a derivation. It is the necessary framework that makes parsing possible. At its core, a context-free grammar is simply a formal mathematical recipe. It provides the exact steps required to generate valid strings of code. The term context-free means that any symbol in our sequence can be swapped out or expanded based on a rule entirely on its own. It requires absolutely zero knowledge of the neighboring symbols to its left or right. To see this in action, watch this empty space. Every language generation process begins at a single obligatory genesis point called the start symbol. Here we'll use express, short for expression. From this root, we apply productions. These are directional mathematical rules that command exactly how a specific symbol transforms. This rule forces our start symbol to split into 3 connected child nodes, an expression, a plus sign, and a term. These productions are active instructions for building structure. As new rules trigger, the tree continues to branch downward. Together, the start symbol and these production rules function as the engine driving the top-down construction of any code block. As this engine expands the tree, it produces 2 very distinct categories of nodes. Notice the pulsing nodes at the bottom edge. These are non-terminals. Think of them as grammar variables or active construction sites. They indicate that the work is unfinished and they can still be expanded by further production rules. Eventually, a final production rule executes, and the branch reaches the absolute end of its path. These locked nodes are terminals. They are the final, immutable symbols, like an identifier or an operator that cannot be expanded. They represent the actual characters that will appear in the compiled code. The entire generation process concludes once a branch consists entirely of terminal leaves. What remains at the bottom of the tree is a mathematically complete token sequence. This schematic organizes the system. You have terminals, the actual symbols, non-terminals, the active variables, productions, the replacement instructions, and the start symbol, the root. These 4 components interact continuously to draw the exact boundaries of a programming language, generating every mathematically valid sentence that can exist within it. So far, we've looked at how grammar generates code from the top down. But when you write a program, the compiler encounters your text from the bottom up. This dynamic creates a strict legal arrangement. The context-free grammar acts as the permanent law of the language, and the parser acts as the inspector, enforcing that law. When you submit a string of code, the parser checks the rules. If it can trace a valid path of productions that successfully generates your exact string, it accepts the code. If it runs out of options and no combination of grammar rules can possibly produce your token string, the parser decisively rejects it. The syntax of every single modern programming language operates entirely on this massive system of context-free grammar. When a parser reads a long, flat string of terminal tokens, it must somehow reverse engineer that raw input back up into a massive, complex syntax tree. The parser relies on specific mathematical processes called derivation and parse tree construction to perform this task. Mapping out those mechanics is exactly where we go next.